Hi everyone, this is Mrs. GA, and today we're going to do a little right triangle trigonometry review. But first, I'm going to ask you to pause video and give this warm-up a try. Alright, so hopefully SOHCAHTOA sounds familiar from geometry. It's just a mnemonic device that we use to help us remember the ratios of our three basic trig functions, sine, cosine, and tangent, which we're going to review today, but here's what it stands for. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this is just to kind of jog your memory so you can have an idea of the type of trigonometry that we're going to be talking about today. So today we're going to be reviewing a few different things that hopefully you remember again from geometry. Pythagorean Theorem. We're going to review our sine, cosine, and tangent ratios, so SOHCAHTOA, just like we did in the warm-up. We're going to talk about using our inverse trig functions, and last we're going to talk about special right triangles. So let's start with the Pythagorean Theorem. So we know that the Pythagorean Theorem helps us to find missing sides of a right triangle like this. So remember, a right triangle is when you have a triangle where one of the angles is 90 degrees. And since the angles of a triangle add up to 180, if one angle is 90, that means that the two other angles are going to be acute, which means less than 90. So the Pythagorean Theorem is a squared plus b squared equals c squared. So the important thing to remember here is that a and b are kind of interchangeable. They're the two legs of your triangle. So this is called a leg, this is called a leg, but c must be the hypotenuse. C must be the hypotenuse, which, if you remember, the hypotenuse is always the leg that is, or the side, that is opposite the 90-degree angle. So it's always opposite the 90-degree angle. So it's really important to remember that the hypotenuse is always C. In terms of your other two legs, it doesn't matter which one you call A and which one you call B. Okay, so let's practice using this Pythagorean theorem. So here you can see we have a right triangle. It is important that you remember that it must be a right triangle to use Pythagorean theorem. If it's not a right triangle, you can't use Pythagorean theorem. So you can see I'm given the two legs, and here we're finding the hypotenuse. So we could say 5 squared plus 10 squared equals c squared. So c is going to be the square root of 5 squared plus 10 squared. And then I like to simplify from here. Now, I do want to point out that when we do the plus or minus, when we take the square root of both sides of an equation, usually we put a plus or minus out front. However, if you look at what we're solving for, this is the side of a triangle, so it's impossible for that length to be a negative number. So it's always just the positive square root here. So c equals the square root of 25 plus 100. So c is the square root of 125. Now for these, it is really important that we try to simplify our radicals when we can. So the square root of 125, well, 125 is simply 25 times 5. And the square root of 25 is 5, so this would be 5 root 5. So remember, always simplify your radicals when you can. Okay, let's try this next one. So here we are given one leg in the hypotenuse, and we're asked to find the other leg. So when we set it up, it's 9 squared plus x squared equals 14 squared. So remember, 14 is our hypotenuse. So if I'm solving for x, we can start by subtracting 9 squared, which we know is 81. I'll simplify it after. So x is going to be the square root of 14 squared minus 9 squared. Again, we're just doing the positive square root because we're finding a length of a side of a triangle. So here we get 196 minus 81. So here we get the square root of 115. Now, you could try to simplify this, but you see the only two factors of 115 are 5 and 23. So there's no way to simplify it. So this is the length of our missing leg. Okay, so I have 2 for you to try on your own. So please pause the video and give it a go. Okay, go ahead and check your work here. So for this first one, again, just make sure that the C value you're using is the 8. And then for part B, the C value is x, which is what we're solving for. And also make sure you simplified your radical for part A. Okay, so now we're going to move on to our basic trig ratios for our 3 trig functions that we're going to be working with: sine, cosine, and tangent. So sine, cosine, and tangent, again, are simply a ratio of different sides of a triangle based on the angle you're working with. And we are going to, for these basic trig ratios, we're going to be working with one of the acute angles of our right triangle. So again, for this, we do need to be working within a right triangle to use these ratios. Okay, so first, let's talk about how to name the different sides of a triangle based on the angle you're working with. So let's say we're working with this angle down here, theta. So just so you know, theta, this is a Greek letter, theta. Theta is how we read it. And it's just a variable that we use to signify an angle. It's probably the most common thing you'll see to show an angle. So if this is the angle we are working with, well, we know that the hypotenuse is always going to be the angle that's across from the 90 degree. Now, the hypotenuse is always going to be one of the sides touching your angle. So the other side that is touching the angle we're working with, we call the adjacent side. We call that adjacent. Adjacent means next to. So again, one of the sides touching your angle will always be the hypotenuse. And so the other side, we'll call that the adjacent side. And then the side that is across from the angle, we call that the opposite side. The opposite side. So it does matter which angle we're working with, because if we were working with this angle up here, this would be the adjacent side and this would be the opposite side. So you just need to be careful that you know where you're starting so you can name the sides accordingly. So the 3 trig functions we're working with, again, are sine, cosine, and tangent. So by definition, sine of theta, so the sine of any angle within our right triangle, will be the ratio of the opposite side length over the hypotenuse. So it's opposite over hypotenuse. Cosine of theta will be the ratio of the adjacent side length over the hypotenuse. And the tangent of theta will be the ratio of the opposite side length over the adjacent side length. So this is the so, and this is the ka-toa of SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Now, I do want to point out, when we are writing these 3 ratios, like within an equation or within our work, we use these abbreviations. So sine we write as SIN. Please still make sure you're reading these as sine, cosine, and tangent. So we still say the full word, even if we don't write the full word. Okay, so let's practice using these ratios. And sorry, my lettering got a little bit scrambled, so let's just start with this first one. So here we're given our triangle with 3 side lengths, and we're asked to find the sine of angle C. Okay, the sine of angle C. So if we are working with angle C right here, I'm going to label the sides. This would be our adjacent side, this would be our opposite side, and this is going to be our hypotenuse. So we know that sine is opposite over hypotenuse. So that means the sine of angle C is simply 21 over 29. So notice how I read it. I said the sine of angle C is 21 over 29. So it's the opposite side length over the hypotenuse. All right, let's look at this next one. Here we're finding the cosine of angle C. So again, we're working with this angle right here. So that would make this the adjacent, this is opposite, and this is hypotenuse. So we know that cosine is adjacent over hypotenuse. So that means the cosine of angle C is 36 over 39. And here, if we can simplify, we should. So the cosine of angle C is going to be 12 over 13. All right, let's try this last one here. So here we're asked to find the tangent of angle A. So here we're working with this angle. So again, this is adjacent, this is hypotenuse, this is opposite. And we know that tangent is the opposite over adjacent. So the tangent of angle A is 12 over 35. So the opposite side over the adjacent side. So there you go. That's how you use your basic trig ratios. Okay, we're going to try another one together. So here we are asked to find all three trigonometric ratios of angle D. So you might notice first that actually one of our side lengths is missing, which we will need to help us find sine and tangent. So before I do anything else, let's see if we can find the length of side D. And just so you know, when you're naming angles and sides, the angles are always named with capital letters, and then the side that's across from it or opposite it will be the same letter but lowercase. So this would be side D. So let's do Pythagorean theorem to help us find that missing side. So we can say 12 squared plus D squared equals 13 squared. So D is going to be the positive square root of 13 squared minus 12 squared. So square root of 169 minus 144 is the square root of 25, which is 5. So this is actually called what we call a Pythagorean triple. Pythagorean triples are I guess triples are groups of three numbers of a right, where the sides of the right triangle are all whole numbers. So there's only so many Pythagorean triples that exist in life because, again, the three sides of a right triangle must work for Pythagorean theorem. So most of the time, one of the sides is going to be some radical, but there are some, again, where they're all three whole numbers. So this is one of them. 5, 12, 13 is what we call it. And again, it's called a Pythagorean triple. Okay, so anyways, so now that we know our missing side, we can find our three trig ratios of angle D. So let's start with sine of angle D. So remember, sine is opposite over hypotenuse. This is going to be our opposite, this is our hypotenuse, and this is our adjacent. So the sine of angle D is 5 over 13. Cosine, remember, is adjacent over hypotenuse, so 12 over 13. And tangent of angle D is going to be the opposite, so 5 over the adjacent, so 12. There's our three trig ratios of our right triangle. Okay, so at this point, I'm going to ask you to pause the video and see if you can find the sine of angle A and then the tangent of angle B. All right, go ahead and check your work. So it is important that you know which angle we're working with because if we're doing the sine of angle A, the opposite side is 8. So it's 8 over 17. But if we're doing the tangent of angle B, now the opposite side is 15 and the adjacent side is 8. Remember, tangent is opposite over adjacent. So it really depends on which angle you're working with when you're deciding which leg is opposite and which leg is adjacent. Okay, so now we're going to try using our trig ratios in a slightly different way. So you can see in all of these examples, we are given one of our acute angles. And then we are also given one side length of our right triangle, and then we're asked to find a missing side length. Now here, I cannot do Pythagorean theorem because I only have one side length, and you need at least two to do Pythagorean theorem. So we're going to need to use a trig ratio. So we are given that this angle is 59 degrees. I do want to point out we could easily figure out that this angle is 31 degrees because the angles must add up to 180. So you do 180 minus 90 minus 59, but let's work with this angle anyways. So if we are given this angle and this leg and this hypotenuse. I know we don't know this leg, but this is what we'll be working with. In reference to the angle 59, we would call this the opposite side, and then we would call this the hypotenuse. So we ask ourselves, which trig function uses opposite and hypotenuse? And that would be sine. So we could say the sine of 59 degrees equals x over 17. And then from here, we're going to solve for x. So if I were solving for x, I would multiply both sides by 17. So 17 times the sine of 59 degrees. I want to point out sine of 59 degrees is just a set value. So when we multiply by 17, the 17 does not go in and multiply to the 59 degrees. Sine of 59 degrees is just a set value. It's some decimal. So you do 17 times the sine of 59 degrees. And then this we're going to plug into our calculator. And it does say round to the nearest tenth if necessary. So we do 17 sine of sine of 59. And we should get approximately 14.6 if you round to the nearest tenth. So you could see that we are able to use our trig ratio to help us find a missing side when we don't quite have enough information to use Pythagorean theorem. Okay, let's try part B. So here I'm working with this angle, and I have the adjacent, or we're trying to find the adjacent side, and then we also have the hypotenuse. So you ask yourself, which trig function uses adjacent and hypotenuse? And that'd be cosine. So we can say the cosine of 27 degrees equals x over 20. So we're going to multiply both sides by 20 to solve for x. And then from here, we're simply going to plug this into our calculator. And we should get approximately 17.8. So there you go. All right, let's try one more together. So again, we're working with this angle. So in reference to the 53-degree angle, we would call x the opposite, and we'd call 12 the adjacent. So which trig function uses opposite and adjacent? That'd be tangent. So we could say the tangent of 53 degrees equals x over 12. Multiply both sides by 12 to isolate x. So x, again, we'll plug this into our calculator, and we get approximately 15.9. So this is a different use of our trig ratios. All right, so go ahead and pause the video and give this one a try on your own. Okay, go ahead and check your work here. So if we are working with this 36-degree angle, B is our adjacent side, A is opposite, and this length of 10 is our hypotenuse. So we could say the sine of 36 degrees is A over 10, and then we can solve for A. And we could say the cosine of 36 degrees is B over 10 and solve for B. Oh, and there is one part that I forgot to finish solving for because we need all of the missing sides and angles. So we do need to actually find angle B. So remember the three angles of your triangle should add up to 180. So we can do 180 minus the two angles we have, so 36 and 90. And that should be angle B. So angle B is equal to 54 degrees. So now we have fully solved this right triangle. Okay, so now we're going to talk about what we should do if instead of trying to find a side length, what if we're trying to find the angle? So for this, we're going to be using our inverse trig functions, which are called arcsine, arccosine, and arctangent. So I know the names are a little bit funny, but I want you to use the correct names for these. Again, arcsine, arccosine, and arctangent. And the way that we denote our inverse trig functions is with this little inverse symbol. So remember, we've done inverses in the past, and the way you denote an inverse function is like this. This does not mean sine to the power of -1. It means the inverse of sine, which is arcsine. This means the inverse of cosine, which is arccosine, and this is inverse of tangent, which is arctangent. So we know that with inverse functions, everything about them flips. The x and the y values flip, the inputs and the outputs flip, domain and range flip. So when we're working with our original function, like sine of theta equals x, the input, which is right here, the thing we plug into our function, is an angle. And then the output here is a value, right? Like in the last example, we would say sine of 36 degrees. Our input was 36 degrees, and our calculator spits out a value. Now for an inverse trig function, again, the input and the output are swapped. So now when we're using arcsine, the input now is going to be a value, and the output now is going to be the angle. So anytime that you're actually trying to find an angle within a right triangle, we're going to be using one of our inverse trig functions to help us do this. Okay, so let's give a few of these a try. So we're going to find the angle with the question mark. So first we're going to, I'll just call it theta when we're setting it up, but we're going to actually set up a trig ratio just using SOHCAHTOA. So if I'm working with this angle and these two sides, we would call those sides the opposite and the hypotenuse. So we could, since it's opposite and hypotenuse, we could use sine. So we'll say sine of theta equals 39 over 44. But you can see in this case, we're finding the angle. We need to know the angle, and we already know the value. So again, this is when we're going to use our inverse trig function. So once you've gotten to this point, we're actually going to swap theta and the value, and then when we swap the input and output, we're going to use our inverse trig function. So we'll say arcsine of 39 over 44 equals theta. And your calculator has these inverse trig functions as well, so you'll see that arcsine is right above sine. So you can plug this into your calculator to get a decimal approximation of the angle. So again, for inverse trig functions, the output is the angle. So according to my calculator, the angle theta would be 62.4 degrees approximately. There you go. Okay, let's look at this next one. So here, again, I'm working with this angle, and I have these two sides. So in reference to the angle, this is opposite. This would be, opposite. And this is our hypotenuse. So again, we can use sine. So we can say the sine of theta equals 26 over 33. But once I'm stuck, right, I need to find the angle. We swap the input and output, and then we can use the inverse function. So arcsine of 26 over 33 equals theta, and then this we can plug into our calculator. We get approximately 52.0 degrees if you round to the nearest tenth. Okay, and then last part C, again, look at the angle and the sides you have. So in reference to the angle we're trying to find, this would be our adjacent side, and this is our hypotenuse. So we can set up an equation using cosine. So cosine of the angle will be 24 over 36. Now we can swap the input and output and use arc cosine. So arc cosine of 24 over 36 equals theta. And then here we'll plug this into our calculator, and then arc cosine is right above our cosine button. And we get approximately 48.2 degrees. Okay, at this point I'm going to ask you to pause the video and give this one a try. So remember, when I ask you to solve, it means to find all of the missing parts of our triangle. All right, so go ahead and check your work here. So the first thing I did was I actually found the length of side A using Pythagorean Theorem, so you should get 7 root 5. And then I found angle A using cosine, or an arc cosine. So I tried to use any information that is given in the original problem, rather information that we find on our own, because if you make a mistake along the way, then it will mess up your answer. So if you use given information, at least you know these numbers are correct. So if I'm trying to find angle A, and I have the adjacent and the hypotenuse, I could say cosine of A is 14 over 21, flip the input and output, and we could say arc cosine of 14 over 21 equals A. So A is about 48.2 degrees. And last, we know that the three angles in a triangle should add up to 180. So we do 180 minus the two angles we know, and that gives us angle B, which is 41.8. Okay, the last thing we're going to review today is what are called our special right triangles. So these are two right triangles that you absolutely just need to commit to your memory. They help us find trig values without using a calculator, which is really nice. But these two types of triangles are extremely, extremely important. And we do need to memorize what they look like, and we do need to be able to recreate them. So our two special right triangles, we call this one a 45, 45, 90 triangle because the three angles are 45, 45, and 90 degrees. We call this a 30, 60, 90 triangle. So for these two types of triangles, again, we want to know the ratio of the sides of our triangle. So for a 45, 45, 90, the two legs of our triangle, we will call those side lengths 1, and the hypotenuse we will call root 2. So that's going to be the ratio, or the ratio of the sides of any 45, 45, 90 triangle. The hypotenuse is always going to be the length of your legs times root 2. So this, again, you need to be able to recreate the 45, 45, 90 triangle, and where the two legs, we'll call them length of 1, and the hypotenuse we say is root 2. And then for a 30, 60, 90 triangle, this is the ratio of the sides. So across from the 30-degree angle, our shortest leg, we'll call that 1. Our longer leg across from the 60, we'll call that root 3. And then our hypotenuse, we will call that 2. So this is the relationship between the three sides. So in reference to the smallest side, the hypotenuse is always going to be double that length, and the other leg is always going to be root 3 times that length. So I just always remember 1 to root 3, and I just remember the smallest side length is across from the smallest angle, and the longest side length, which is 2, is across from the largest angle. So again, these you absolutely need to memorize and be able to recreate them quickly because we're going to use them a lot this unit. Okay, so we're going to try solving these triangles, so finding all of the missing parts without using a calculator. So when you see a special right triangle, like here we see a 45, 45, 90, I'm actually going to draw my own 45, 45, 90 kind of nearby, and I'm going to try to draw it with the same orientation. So I'm going to try to draw the angles in the same relative position, like this. And then I'm going to mark up my own, always the same. The legs are always 1 and 1, and our hypotenuse is root 2. So what I've just created here are what we call similar triangles. So if you remember from geometry, similar triangles are two triangles that have the same 3 angle measurements. So we care about similar triangles because while the angles are the same, the sides aren't going to be the same, but the sides are proportional. So if we have two similar triangles, we can find missing sides by creating a ratio. So what I mean by the side lengths are proportional is the sides that are in the same relative position are proportional to each other. So I like to kind of highlight or color code which ones go together. So I can see that the 5, our hypotenuse here, will go with root 2. They're in the same relative position. And if I'm trying to solve for x, we can see that x is in the same relative position as 1. And we know for a 45, 45, 90, both side lengths are the same because this is an isosceles triangle. So if I find this side length, I know this side length as well. So when we set up our proportion, find the value that we know. So we know this is 5, and then we're going to match it with its corresponding side length. So 5 goes with root 2, and we could say equals x over 1. So it's just important when you're creating your ratio that you're just consistent of which triangle goes on top and which triangle goes on the bottom. So I did this over this equals this over this. And then we're just going to solve for x. So here this is just x. X is just 5 over root 2. And then the last thing we need to do for this one is rationalize. So we need to multiply our expression by root 2 over root 2, and we get 5 root 2 over 2. So that's the length of both legs of this triangle. Okay, now let's try one with our 30, 60, 90. So again, if this is 90 and this is 30 or 60, this must be 30. So I'm going to draw my own 30, 60, 90 triangle, kind of with the same relative orientation. Here's my 60-degree angle, here's my 30-degree angle, and we always mark it up in the same way. The short leg is 1, hypotenuse is 2, longer leg is root 3. 1, 2, root 3. And now we can set up our ratios because the side lengths are proportional. So I see that 15 is going to go with root 3. I see that y goes with 1, and I see that x goes with 2. So let's solve for x first. So we're going to start with the proportion we know. So we know that 15 goes with root 3, just as x goes with 2. And now all we need to do is solve for x. So I'm going to multiply both sides by 2, and then we're just going to rationalize. So we multiply by root 3 over root 3, 30 root 3 over 3, and then sometimes we do need to simplify a little more here. So our x value is 10 root 3. Then we're going to do the same thing to solve for y. So I start with our original proportion, 15 over root 3. I would always, again, try to use the information that is given rather than information we found, because what if we made a mistake? So 15 goes with root 3, just like y goes with 1. So y is actually equal to 15 over root 3. Again, we need to rationalize, and we get 15 root 3 over 3, and this one, again, we can simplify a little bit more. So y equals 5 root 3. So again, if you know your special right triangles, you can draw your own, and then using the fact that they are similar triangles, we can create ratios of the corresponding sides to solve for missing sides. Again, we can do this completely without a calculator. We don't need to use SOHCAHTOA. So anything with a 30, a 60, or a 45, I will be expecting you to do that without a calculator. Okay, I have 2 for you to try on your own, so please pause the video and give it a shot. Okay, go ahead and check your work here. So you can see for each problem, I drew my own special right triangle with the same relative orientation, and then I just set up ratios with the corresponding side lengths. All right, here's the last 2 for you to try on your own. So for last time, please pause the video and give it a try. All right, so check your work here. And again, just make sure that with your own special right triangles that you drew, that you have the correct numbers in the right place. So the 2 legs are always 1 and 1, and our hypotenuse is root 2. All right, so that is all for today's video. Thank you guys so much for watching.